Hello and welcome to this lecture. In this lecture, we are going to start talking about the adjoint of an operator. So, this is a very important and interesting idea. All of you may have learnt about the transpose of a matrix. So, this adjoint of an operator is connected to that, and we are going to talk about that in this lecture. Okay. First thing is, we will start with the inner product. We will see the inner product plays a very crucial role here. So, if you look at the inner product, I have u is u1 u2, v is v1 v2, and u dot v is u1 v1 bar plus u2 v2 bar. Okay, this is the inner product. So, what is the linear transformation here? Why is inner product connected to linear transformation? Here is the idea. Okay, if you fix v, let us say v is some fixed vector, it is given to you, it is fixed, and you consider u dot v as a mapping from u to u dot v. Okay, for every u I go to u dot v for u in C2, right? So, for every u I go to u dot v, v is fixed. Okay, so this gives me a linear transformation. Okay, for a fixed v, the mapping u in C2 to u dot v in C is a linear transformation. Linear transformation from C2 to C. Okay, this is not quite an operator, right? It is a linear transformation from C2 to C. Okay, so proof is really trivial. It just comes from the linearity of the inner product in the first argument. Just write it down. You will see if you take a linear combination of Ax, u as a linear combination, that's the distributive property will give you the answer. Okay, so here is an example. Supposing I fix v as 1, 2, then u is then this mapping, this linear transformation mapping goes from u to u1 plus 2 u2, right. So, u in coordinates u1 u2, it goes to u1 plus 2 u2. Okay, notice how the coordinates play a role here, right. So, that is something when you talk about inner product, the coordinates will come in naturally. So, you have to think of the canonical basis here. So, v is 1, 2 in the canonical basis. Canonical basis is what you can use here. Then u is u1 u2, and then that goes to u1 plus 2 u2, right. So, it is a dot product with 1, 2. Okay. So, if you have a complex case 1 plus I 2 minus I, then u will go from u1 u2 to u dot v. So, this will get conjugated. So, you get 1 minus I u1 plus 2 plus I u2. Okay, simple little linear transformation from the inner product. Okay. So, once you have a linear transformation, you can also have a matrix, right. Every linear transformation is a matrix, isn't it? Matrix, isn't it? So, it goes from C2 to C. So, this will be a 1 by 2 matrix, isn't it? So, the fixed V you take go from u to u dot v is linear transformation. What is the matrix of TV with respect to the canonical basis? 1, 0, 0, 1. Okay. So, if E is 1, 0, what happens? E is 0, 1, what happens? This will define the canonical basis, and you are going to see. So, the output is just 1. So, it will be a 1 cross 2 matrix. Okay. And the 1 cross 2 matrix M of TV, the first guy is the output when E1 is the input, and that is E1 dot V. The second column is the output when E2 is the input, and E2 dot V is the answer here. So, M of TV, the matrix of this linear transformation representing the dot product with a fixed V, is simply E1 dot V, E2 dot V. Okay. So, it is a 1 by 2 matrix. Okay. What do you do with the matrix? With a matrix, you can evaluate the inner product also. Okay. So, supposing you have a U is U1 U2, u dot v is the same as m of tv times u1 u2. Okay. So, now this gives you a very interesting little property here. So, in m of tv is this vector here. So, if you have v is 1 2, what is m of tv? It is just e1 dot v, and e1 dot v I know is the first coordinate 1, e2 dot v is the second coordinate 2. Okay. So, it is easy enough. So, if v is 1 plus I 1 2 minus I have to do e1 dot v, but remember the conjugation will happen here because I have got a dot v here. So, you get 1 minus I 2 plus I. Notice this conjugation, it happens only in the complex case. In the real case, it is very, very simple. So, m of tv is a 1 cross 2 matrix. So, inner product can be evaluated as a matrix multiplication. The matrix multiplication that you have is the matrix of this inner product, and that is just the conjugate of that vector written as a row vector, right. So, this is easy little property. Okay. So, this leads us to the definition of something called the conjugate transpose of a vector. Supposing you have V is V1, V2 and C2, the conjugate transpose of V, this is denoted VH. Okay, what is VH? V Hermitian. Okay, so fancy name for this very simple operation, it is V Hermitian. It is nothing but the matrix 1 by 2 matrix V1 bar, V2 bar. So, notice this curious little thing, V is a column vector, and then V Hermitian becomes a row vector and conjugated. Okay. So, that is why it is called the transpose. Transpose is you are transposing the column into a row. Okay, that is the notion of a transpose, and conjugate comes because you are taking conjugate. So, V Hermitian is conjugate transpose. Okay. what is the defining nice little property of this conjugate transpose? U dot V is nothing but V Hermitian times U. V Hermitian is just the matrix of this M of TV times U1 U2. We know that that evaluates the inner product. Okay, it's very easy to see that it evaluates the inner product. Okay, so here's an example. Supposing you have V is 1 2, U dot V is 1 2 times U1 U2, so U1 plus 2 U2. Silly enough, right? So very simple. V is 1 plus I 2 minus I, U dot V is just the conjugate V Hermitian times U1 U2. Okay, so remember this for the inner product. This is a very, very useful relationship for inner product and matrix multiplication. Okay. Now, if you specialize to R, if instead of C2 you are in R2, then this word conjugate is dropped. Okay. So, the transpose of a vector, which is denoted Vt now, which is V transpose, is simply V1 V2. There is no conjugate. Well, conjugate is there, but then it does not do anything. So, you can drop the conjugate and simply say transpose of V. Okay. So, this is a very brief introduction to the transpose and conjugate transpose. This concludes this very brief lecture. In the next one, we will take up this notion of adjoint of an operator. Thank you very much.